You know that feeling when you're walking down the street, right? You walk out of your house, your phone switches from Wi-Fi to cellular, and yet that high-definition video call you're on just keeps right on running? It doesn't even stutter. How exactly does a global network sync your audio, your video, and your data across totally different devices without dropping a single frame or losing a single packet? Well, today, we're going to tear down the invisible, hyper-fast infrastructure that literally makes this modern miracle happen.
Welcome to The Explainer. Today, we're doing a full systematic teardown of the IP Multimedia System. Most people just call it IMS. This is the absolute bedrock architecture that telecom operators use to deliver Internet Protocol-based services to mobile users all over the world. And look, we aren't just skimming a theory today. We're going to get right under the hood and look at the exact SIP signaling, the component handshakes, and even some of the real code that makes this entire engine operate. Let's jump in.
So, here's our roadmap for today. First, we'll look at the IMS big picture. Second, we'll meet the core components. Third, we'll do a deep dive into SIP synchronization. Fourth, establishing a live session. And finally, service continuity and handoffs.
All right, kicking things off with Section 1, the IMS big picture, bridging voice, data, and multimedia.
Think about communication before IMS. It was all stuck in these different, isolated silos, but IMS unifies everything into a very strict three-layered architecture. Down at the bottom, you've got the transport layer. That acts as the physical entry and exit point, using protocols like IPv4 or IPv6 just to route the packets. Then, right in the middle, you have the control layer. This is the absolute brains of the operation, where all the SIP signaling and session coordination actually happens. And finally, sitting at the top is the application layer. That's where you'll find the SIP application servers that generate the real services, executing real-time logic for things like VoIP or rich multimedia.
Moving right along to Section 2, meet the core components, or what I like to call the postal system of telecom.
Okay, so operating inside that middle control layer is something called the Call Session Control Function, or CSCF for short. I want you to think of this as a perfectly synchronized postal system. First up is the P-CSCF. This is essentially your local postbox. It's the absolute first point of access for your device, establishing an IPsec security association. It forwards your messages, but it doesn't actually authenticate you. Next is the I-CSCF. Think of this as the regional sorting facility. It acts as a gateway, querying the master database just to figure out where you are. And finally, the S-CSCF. This is the central headquarters. It verifies your identity and actually executes the SIP routing logic to trigger your services.
Now, the S-CSCF can't do all this alone. It relies completely on the Home Subscriber Server, or HSS, which is basically the master database. It holds your subscriber profile and all your cryptographic authentication keys. But how do these nodes stay synced? Well, they communicate using the diameter protocol over a specific connection called the CX interface. Whenever your location or your permissions change, the HSS pushes an exact, real-time diameter update directly over to the S-CSCF. That ensures the network's routing tables are perfectly synchronized at all times.
Section 3, time for a deep dive into SIP synchronization and the registration handshake. So for you to actually receive calls, the network has to know your exact IP location. When you power your device on, it generates a literal line of code, a SIP register request. It shoots this over to the P-CSCF, which passes it down the chain to the S-CSCF. But here's the kicker. The network intentionally rejects your first attempt. It fires back a 401 unauthorized challenge.
Now don't worry, this rejection is totally by design. It's all about strict security. That 401 unauthorized message contains a www authenticate header, which is packed with a random cryptographic challenge generated by the HSS. Your device gets this, passes the challenge down to your physical SIM card to compute a secure response using what's called the AKA algorithm, and then it resends the register request, but this time it includes an authorization header with the correct mathematical proof. The S-CSCF verifies the math, and boom, grants a SIP 2.0 200 OK message. You are now securely synced to the network.
All right, Section 4, establishing a live session. Let's route a call.
So you're registered. Great. But how do we actually route a live multimedia session across the globe? It all kicks off when you initiate a call, which generates a SIP invite message. Tucked inside the body of this message is the Session Description Protocol, or SDP. This is literal code that looks something like M equals video 49170 RTP/AVP. Essentially, your phone is telling the network, hey, I want to open a video stream on port 49170 using these specific video codecs. This invite message travels right through your local P-CSCF up to your S-CSCF, looking for the person you're trying to call.
From there, your S-CSCF forwards that invite to the receiver's I-CSCF, which then queries its own HSS via diameter to find the receiver's current S-CSCF. And as this invite hops through all these different nodes, it literally leaves a breadcrumb trail using record route headers. The receiver's device inspects your SDP code, agrees to the video codecs, and fires back its own 200 OK. You send an ACK to acknowledge it, and just like that, a synchronized peer-to-peer media stream is established. And the craziest part? All of this logic happens in a matter of milliseconds.
Which brings us to Section 5, Service Continuity and Handoffs, how we never drop the call. Because let's face it, we don't just sit still. We're constantly switching networks or transferring a video from our phone to a smart TV. How does IMS maintain this? It uses an incredibly advanced feature called collaborative sessions. By firing exact SIP refer or update commands, IMS actually allows multiple media flows to be transferred, or even split, across entirely different devices on the fly, all while keeping the person on the other end of the line completely uninterrupted.
Inside one of these collaborative sessions, your devices actually take on very strict, logical roles to prevent data collisions. One device acts as the controller user equipment, or controller UE. This is the master node. It issues the SIP commands to add or transfer media. The other devices act as controller UEs. They're subordinate. They just accept the real-time media packets pushed to them, and they can only release the specific media that's terminating on their own screens.
But the real magic? That happens back up at the application layer with the SCCA, the Service Centralization and Continuity Application Server. It acts as this invisible anchor, technically operating as a back-to-back user agent. When you switch networks, the SCCA quietly replaces your old source access leg with a brand new target access leg by rewriting the SIP headers on the fly. And because the SCCA terminates both ends of the connection, the remote party maintains a single continuous session. They're totally unaware that a massive, complex network handoff just occurred.
Let's do a quick recap of this engineering marvel. First, IMS unifies our communication via a strict three-layer architecture. Second, the CSCF components act as the routing backbone, communicating via protocols like diameter to accurately locate users. Third, exact SIP code snippets, like the register, the 401 unauthorized challenge, and the SDP payload negotiations, dictate perfect synchronization. And finally, the SSCAS uses back-to-back anchoring to enable completely seamless media handoffs, no matter how much you move around.
The engineering behind a simple video call is just absolutely breathtaking when you break it down. But you know, technology never stands still. As we push toward even richer, incredibly data-heavy, immersive experiences like real-time augmented reality telepresence, the demands on our networks are going to multiply exponentially. So I want to leave you with this to consider. As internet protocols continue to evolve, how will the IMS architecture have to adapt to secure and synchronize the next generation of instantaneous, immersive global communication? Thank you so much for joining me on this explainer. Keep wondering, keep learning, and I'll see you next time.